posters. They're informing you
Recording in progress.
with example designs, go-free problems, and many variations in our research. And they are all registered to the HKI, Intellectual Copyright. They are already registered and granted the intellectual copyrights. So, okay, there is a QR code on the corner, or you may see the details of the information from our social media. Any questions about the symposiums, please ask it later on at the end of this session, because now the microphone is already on for the Zoom meeting, and if it is possible is it possible for me to greet the audience in the Zoom meeting? Yeah. Where is the camera? Is it there? This is the camera. Halo Bapak Ibu yang online, apakah mendengar suara saya? Am I audible? We are starting very soon, so hopefully you are already settled and ready to follow the discussions in the second sessions with Paul James. Okay. So it is our honor to have Paul James talk this afternoon. In the second sessions, he will describe to us how we develop cognitive load theory. So what kind of research, how we run our research, how we design our research, and how we gain insights from the research results. You have time until 2:30 and discussion up to 3 p.m.
Sure.
Yeah. Okay. We are already full with our lunch. So in the middle, if you can help us to relax again, that would be great. Okay. Anyway, I saw some books on your table.
Yep.
So
no, they're for later.
Table later. I thought it's for giveaway.
No, it's for you.
That's for me. Oh, that's very generous. Thank you, I appreciate that. Okay, so before further ado, Paul James, please, your floor is yours. Are we giving him big applause to start?
Terima kasih. Maybe we, after the big lunch, maybe we start with a refresher. How about we all stand up? Standing up. Okay, just moving around. There we go. Big stretch, getting the blood moving into our brains, around our body. Fantastic. So I will remember to do more of these during the day, just as much for myself. Okay, please be seated. Okay, so quick recap. In the first lecture, we learned about cognitive load theory and load reduction instruction, and the many principles of cognitive load theory in particular, and what are called instructional design effects, such as the split attention effect, the worked example effect, the redundancy effect, my personal favourite, the imagination effect, the list goes on. All of these effects have been generated from cognitive load theory, but then, importantly, tested through educational experiments. And that is a very important feature of the scholarship of cognitive load theory, that the theory really does emphasise the use of educational experiments of various kinds in order to test the ideas that flow from the theory. So in this lecture, I want to help you learn more about what does it mean to conduct an educational experiment, and what are some of the design principles for good quality educational experiments. Many of these design principles that I will discuss come from my own research, things that I have learned in, gosh, how long is it now? Over 25 years of conducting educational experiments. And so I hope that what I've learned will be of use to you if you conduct educational experiments. I know that some of you have already conducted educational experiments. Can I see hands up for people who have worked with Miss Ender to conduct educational experiments? Okay. Surely there's more than just one person. Two, thank you, Iqbal. Yeah, it's going like that. Yeah, okay, good. So, for those people who are already conducting educational experiments, I hope that you may learn something new. And for people who have not conducted educational experiments, I hope that I will inspire you to consider this method for generating new knowledge about how we can teach and learn effectively. So that's my goal. Again, everyone, if you have questions during the lecture, please just put up your hand and ask. Okay? All right. One of my favourite educational researchers is this man, Lee Cronbach, very, very famous in educational psychology for a number of reasons. Incredibly big brain, massive big brain. He was an expert in not only statistics, but also educational research methodology and substantive educational research. Very famous, amongst other things, for Cronbach's alpha, which you might have heard of, a measure of reliability of a test. And also on the education side, what's called an aptitude treatment interaction. And we've seen an aptitude treatment interaction in the first lecture in talking about the expertise reversal effect. The expertise reversal effect is an aptitude treatment interaction. In other words, what works best? It depends. It depends on the interaction between the learner and the instruction. So, very, very famous educational psychologist. And I love this quote because it reminds me of what my job actually is. Our job, Anders and my job, and if you choose to do psychologically informed research, your job too, is to invent constructs and to form a network of laws which permit prediction. So what does that look like in cognitive load theory? Well, we might invent a construct such as extraneous cognitive load, and we may put that construct within a broader network of constructs such as cognitive load theory or schemas, working memory, long-term memory, and we predict that by reducing split attention, we reduce extraneous load and therefore we support learning. So just as one example of this way of thinking about what the job of educational researchers is. So I just wanted to start with that high-level statement of what is our job, and I think this covers it quite nicely. Just to point out, so just focusing on this statement, a network of laws, that covers a lot of ground. We might say a network of principles, a network of understanding more generally, and to give you some examples of these networks. These are basically theoretical models. Let's see a couple that we've seen before. Load reduction instruction model. This is an example of a theoretical framework that makes predictions about successful learning. What order should we provide, or what order should we use specific pedagogies in order to optimise cognitive load in relation to what students already know? So an example of one theoretical model that we've already seen. Here is another theoretical model. Richard Mayer's model of human cognitive architecture, specifying a range of constructs and relationships between constructs in order to generate predictions about high quality teaching and learning. So this model argues that if we provide students with opportunities to select words and images, organise those words and images into a coherent working memory model that can be integrated into long-term memory, then we will support learning. But we need to do that without overloading working memory. So just another example of a theoretical model that generates predictions that we can test empirically. And when we look at good quality educational research, we see these same features, that there is a theory or a theoretical model or a theoretical framework underlying our work, and that we may use particular parts of that model to generate hypotheses and then test those hypotheses. I should say that sometimes our predictions don't work. Sometimes our hypotheses are not supported. And that may be disappointing, but it is all part of the scientific method. So there's an old saying, if the facts don't fit the theory, too bad for the theory. Our theories, when we use a scientific mindset, we test our theories. We don't just assume that our theories are correct. And over time, sometimes theories fail. Sometimes theories die because the evidence grows and grows and grows against the theory. And the theory must change or adapt, or sometimes die. And that has happened in educational research. Behaviourism, for example, is a broad theoretical model that was very, very popular in some educational settings, particularly America. But over time, the evidence against behaviourism as a general model for human thinking just became too big, too much evidence against it. And so that's where we began with a more cognitive view of human psychology, and that has flowed through into education. Everyone, I want to just set the stage for this thing called science. What do we mean by science? So I'm going to provide a few definitions for you to read. So can I invite you to read this excellent definition? So we see some relationships between what's on screen here and what Lee Cronbach said. So I'm just going to quickly go back to Lee Cronbach. So Cronbach talks about a network of laws. Okay, where do we see network of laws? Hypothetical propositions about presumed relations. That's another way of saying network of laws. But this definition goes a bit further in talking about the nature of scientific investigation. Scientific investigation is systematic. It's programmatic, that we build our knowledge study by study by study. If we do bad research, bad science might be, oh, let's look at that thing, then let's look at that thing, then let's look at that thing, then that thing. No clear relationship between all of those things. Every now and again, maybe once a century, there will be big scientific research that completely changes how scientific thinking works. So, for example, do we have any physics researchers? Physics? Okay, so an example would be the shift from Newtonian physics to quantum mechanics. Massive, massive change in the fundamentals of the theory. In biology, the change from pre-Darwinian to Darwinian considerations. So the theory of evolution was world-changing. So every now and again we do have massive, massive changes, but usually, certainly in my work, it's the ambitions are a bit smaller than world-changing. They're programmatic or systematic changes in learning about a phenomenon. This word is very important, critical. Science is hard. Science is hard because we have to think about alternative explanations for our findings. We need to be critical of our own findings. We need to be prepared to consider alternative explanations. And for those of you who have done peer-reviewed research, when you get feedback from reviewers, and they will be critical, and you need to think carefully about their considerations. So this whole activity called science essentially is a very careful and thoughtful and critical process of generating new knowledge that is based in evidence. And that's where we got empirical. So we don't simply make arguments based on pure logic, pure argument. We actually generate facts and see whether those facts fit with our theoretical predictions. On screen here, we see some further description of the process of doing empirical research. Please, once again, have a read through and I'll make some comments. So a few things for me to point out. There is a place for logic. Absolutely, there is a place for logic, for careful argument, but we go beyond just careful argument. because it's evidence-based. We need to provide evidence for our chain of reasoning. We need to use methods that are appropriate to the questions that we want to ask. And so, as I will develop this argument further, if we want to ask causal questions, does using this method lead to better learning than this method, which only produces learning at this level? So this causes that. Experiments, educational experiments, are really well suited to asking causal questions. There are other questions we can ask in educational research, but many other methods don't work so well for answering causal questions. And so that's why people like Enda and myself really like doing experiments, because we want to answer causal questions. So we need to use experimental designs that are suitable to the questions that we're being asked. And indeed, we want to give thought to how far can we generalise our findings? How strong are the claims that we can make about the findings that we have? If I find some results with this group of students, can I generalise to all students of every age, in every nation, in every culture, in every educational setting? Well, I should probably be a lot more careful in my claims than saying, look at this everyone, this is amazing, everyone should do this. So as an example of that, imagine if you find some findings in primary school mathematics, can we generalise those findings to university physics? Might be a bit questionable, a bit dangerous to generalise from that setting all the way to this setting. And these are the kinds of careful thinking that we need to engage in. And lastly, we need to use suitable analytic methods and collect suitable data for answering our questions. So this definition of scientifically based research comes from the American Educational Research Association. I think it's, I agree with this basic definition. Okay, a little bit of fun. A new word, a new noun for you. Apophenia. Apophenia. It is a very human tendency. Remember I talked in first lecture about we are constantly trying to make sense of the world, okay? And that we seek to understand patterns in the world. Often those patterns are meaningful. So, what does this collection of squiggles on the screen mean? Well, you know, can we read it? Yes, we can. Sometimes, however, the patterns that we observe in our environment are not meaningful, but we ascribe meaning to them, and that's apophenia. So, what does this look like to you? What does it look like? A cloud, but does it look like something else? A duck? For me, it looks like kind of like a man. Do you see what I mean? Maybe I'm just imagining that. Let's try another one. That one's not so, doesn't, oh, kind of. What, do you see something in this? Does it look like a face, maybe? Can you see a face? How about this one? This is from Mars, the planet Mars. Very famous because of that. Again, some people might say, oh look, it's a face, and indeed in Earth's moon, when we look at the moon, sometimes we see a face. We see patterns where they don't exist. Apophenia. Why am I mentioning this? Well, part of the reason that we do educational research and psychological research more generally is to stop us from seeing patterns when they don't exist. Part of the reason that we, as a world society, have invented statistical methods is to try and understand patterns in data and make decisions about whether those patterns are meaningful, or are the patterns not meaningful, or is there no pattern at all? As some examples, on screen here we see scatter plots. Basic statistical method. Plotting data against each other. So a value on this variable, a value on this variable, where do those values intersect? When two variables are perfectly correlated, the data looks like this. This never happens in human data. There is always some noise in the data. When two variables are strongly correlated, the pattern of data might look like this. A correlation coefficient of 0.80. Very strong correlation. Again, unusual in human data to get such a strong correlation. Often in correlational research with people, it might be more like this, a value of about 0.30, still a pretty strong relationship. Completely uncorrelated, a correlation of 0. Just a big old cloud of data, no clear pattern in the data. Correlations can also be negative. So I think you would see, I think you'd agree, there is something different in the shape of these scatter plots compared to these ones, or at least this one. In this one, as we go up on that variable, there tends to be an increase on that variable, so a positive correlation, whereas the pattern that we see in this data is opposite. As this value goes up, this value goes down, resulting in a negative correlation, whether that's relatively smaller or relatively larger. So that's correlation. That's correlational data, often used in psychological research and educational research. But when we do experimental research, we take a bit of a different view of correlation. We're still talking about correlation of a sort, but we're wanting to make causal claims from correlation between one thing and another thing over time. So this is some actual experimental data from an experiment from a few years ago. 3 groups, and so in asking that question of are there patterns in the data, the question becomes, are the differences, the mean differences, the average differences between these three conditions enough to get excited about? Do we conclude from the patterns that we see in this data that there are real differences? Because if we look at them, there's overlap between the groups. You know, some of these ones are higher than others. There's, you know, a fair bit of overlap. This group seems to be a little bit higher than this group, but are these two groups different? And this is why we need suitable statistics to make that decision. Are these differences enough to get excited about? So try and keep this data in mind, these patterns, and I'll show you this one. Are these differences enough to get excited about? Is the pattern in the data clearer than in this one? I would suggest that this pattern is clearer. On average, this group seems to have a lower average score than this group, and this group has a higher average group than this one or this one. So a clearer pattern in the data. But I still need suitable statistical methods to make that decision. I don't just look at the data and say, hooray! When we conduct educational experiments, there are some fundamental questions that we want to get answers to, and we see them on screen here. So under conditions of uncertainty, under conditions where people vary, sometimes really a lot, does one approach to teaching or instructional design work better than another? So the fundamental question, does it work? That's a question of effectiveness. But when we conduct high quality educational research, we're asking another important question of why. Why is that the case? And that's a question that we need theory for. So, how and why does it work? We can ask these questions about a range of different educational considerations. We might ask questions about different teaching strategies, different learning activities, different instructional designs, which is where Ender's research comes in and my research comes in. But we can even ask questions about whole educational policies. If we do very ambitious, large-scale educational experiments. As an example, it seems obvious that smaller class sizes will result in better learning. Okay, very, very common belief. Fewer children in a class should result in better education. But is that true? Some large-scale experiments, particularly in the United States, but in other experiments, have actually done the work to test that hypothesis. It takes a lot of work. Many, many students, many, many classrooms, complex statistical analysis. But that's an important policy-relevant question that we could get answers to. Interestingly, the evidence base for smaller classrooms leads to better learning, actually very weak. Yeah, it's very counterintuitive very surprising or paradoxical that the benefits of smaller class sizes are actually not that easy to find. Maybe it benefits certain groups of children much, much more than others. And that's important to know, because educational resources, time, money, number of teachers, number of classrooms, these are all very limited. Imagine if we just said on pure argument, of course we should have, class sizes of maximum 10 children. Imagine that. Think about your average class sizes in Indonesia or in Australia. If we had a policy that said only 10 children per teacher, what would we need? We would need many, many, many more teachers, and we would need many, many, many more classrooms. Where is the money? Where is the space to do all of those things? The educational or the economic implications would be very, very great. And so sometimes it's important to test these questions, because the financial and economic and social implications are very great. So, these are the kinds of questions that we can ask, and just begs the question, I've talked about conditions of uncertainty. Uncertainty often comes because of variability or variance in our students. So my question to you, why do students vary in their learning outcomes? What are some of your ideas? Maybe you turn to each other and compare your answer to this question with each other. Okay, I'd like to hear just a couple of answers to this question.
Thank you. My name's Ayu from Music Education Department. I think why do students vary in their learning outcomes? Maybe different motivation, different ability.
Yep.
I think like that.
Thank you. So, different motivations, different abilities, two very important sources of variability. Other ideas?
They have different prior knowledge.
Exactly, thank you. Building on lecture one, different levels of prior knowledge. There's another, yep. Sorry.
Maybe for a special for Gen Z, Generation Z, is depend on their mood.
Their mood, okay.
Mood, yeah.
Yep. So the answer to the question might be mood, and so I would suggest that all people might depend on their mood.
Especially Generation Z.
Okay. So that's an empirical question. Do some groups vary more, some generations? Maybe. Could be. One more. Do we have, I thought I saw a hand up over this side. Okay.
They have different learning experience.
Yes, absolutely.
Some students maybe have known more than the other students.
Yep. Thank you. So different learning experiences, and we might relate that to prior knowledge. So look, there are many potential answers to this question. Here are some of mine, some of which you've mentioned. So we see prior knowledge, we see general mental ability, also how people think about their own abilities. You might have heard fixed versus growth mindset as a construct, and many others. Personality, random fluctuations of attention. You know, after lunch, maybe we are, more tired. Think about how students behave after recess or lunch from running around in the afterwards. So people vary both within a day and across the day or weeks. Developmental changes, and indeed, what teachers do. Some teachers will have different teaching styles, more experienced, less experienced, different approaches to discipline. The list goes on. So many, many, many sources of variability that might explain why students learn the way they do or how much they learn. And that presents a challenge for educational research, a big one. Educational experiments need to take into account these sources of variability in testing ideas. Philosophers have thought about these questions of causation for many hundreds of years. In a classic statistics textbook, Cook and Campbell summarised these arguments about causation as follows: that if we want to make causal claims, we need to meet 3 conditions that we see on screen here. That there must be a clear sense of covariation or correlation between a cause and an effect. The cause has to come before the effect. We can't travel back through time. Okay, so cause has to come before an effect. And here's where the critical thinking comes in. We need to rule out alternative explanations for the pattern that we see in the data. Look, this is kind of, I hope this captures it nicely. Just have a quick read of this cartoon. So this cartoon is a bit of a joke about how hard it can be to actually, if we think carefully about why things are the way they are, how hard it can be to actually attribute a cause to an effect. It's difficult. What is this thing called an effect, anyhow? Let's just dig into that a bit. So, coming back to my points about apophenia earlier on, we may think that we are seeing an effect, but maybe that effect is actually imaginary. Maybe we are fooling ourselves. Maybe the differences that we see between students can just be attributed to chance differences. So if the effect is real, how large is that effect? Is it trivial? Or is it sort of medium size? Or is it something where you go, oh wow, that's a big effect on learning, or on students' cognitive load, or on students' motivation? Hopefully we can find large effects, often a bit more difficult. But even smaller effects can be important. Imagine a small effect that is very, very cheap, very simple to implement, that every child in the entire world could benefit from, even if it's a small effect, that's a good thing to do. That's a useful piece of knowledge for teachers to have. Coming into useful. Okay. And so this is the fundamental question. When we conduct educational research, particularly educational experimental research, is the effect large enough for us to conclude that this is not just a chance effect. It's not just due to random variability. Okay, sorry, we don't really need to look at that. A bit more about the idea of an effect. Sometimes the measures that we use are meaningful in themselves. So everyone understands what weight is, or height, or strength. Okay, these are meaningful in themselves. Number of calories burned if we're doing exercises. In educational research, we use a very wide range of measures, very wide range of tests, very wide range of self-report measures, like questionnaires. And so very often we used what are called standardised metrics. So we don't use the original metric of, a test score on 1 to 5. We use a standardised metric. A very common one that we see is this one. A relatively simple calculation, Cohen's d. We calculate it as follows. We take the average score achieved by an experimental group and the average score achieved by a control group. Maybe that's how we usually do things and we want to try something different with our experimental group. So experimental group minus control group mean scores divided by the average of the standard deviation of both groups. So let's do a little bit of calculation. Imagine if the experimental group's score was 4 and the control group's score was 2. Both of the groups had standard deviations, a measure of spread, of 2. What would D equal? How would you calculate that? I'm going to ask the mathematics educator. What's the value of D here? Exactly, well done. So that's our value of this measure of an effect. Okay, so it's a standardised measure. These measures, we might calculate this for many different things. Maybe these are test scores. Maybe these are self-reports of cognitive load. Maybe they're measures of motivation during a lesson. We can use this general effect size, this notion of an effect size, to communicate to a wide range of people so that we have a shared sense of the effect size. I'm getting a little bit more technical here, looking at some of the statistical methods that we use. The idea of analysis of variance is very commonly used. The method of analysis of variance is commonly used in educational experiments. You might have heard of a t-test. That's the most simple version of analysis of variance when we just compare two groups, say experimental group and control group. If we have 3 or 4 or 5 groups, we start to need more complex analytic methods, analysis of variance across multiple groups. In essence, analysis of variance seeks to partition or separate out two fundamental sources of variance. One is the variance that we think is happening because of what we have changed, the independent variables. And then there's a whole bunch of other variance that we don't understand, error variance. And we are basically seeking to look at the proportion or the ratio of this variance versus that variance. When we conduct educational experiments, certainly the kind that happen in cognitive load theory, we want to arrange a situation where we create groups that are equivalent as possible before running the experiment. The main way we do that is by random assignment to conditions. We can randomly assign children to conditions or people to conditions in a range of different ways. We might just flip a coin to assign people to different conditions. Other ways include using lists of random numbers, and we use those lists to randomly assign people to groups. In doing so, on average, and with large enough samples, we will create groups that are equivalent with respect to a whole range of different sources of error variance. So remember, just let's go back to this list. The idea with random assignment to conditions is that by randomly assigning people to conditions, the two groups, at least two groups, will be roughly equivalent across all of these different sources of variability and all of the other ones with a large enough sample. If we only have small samples, the risk increases that they won't be equivalent. But with large samples, the risk goes down. And so, if we have successfully created equivalent groups, then we do an intervention and then we test the effects of that intervention. Any difference between the groups can be attributed to our independent variable. It's a very, very powerful way of thinking about causation. Under conditions of uncertainty, can we say this thing caused that thing? Randomised controlled trials are one of the best methods, probably the best method, for answering causal questions, including in education. So random assignment to conditions is one way of dealing with variation between students that might otherwise explain our results. We can do some other things in our experiments. We might collect data about one or more of those pre-existing sources of difference. And so I've emphasised, actually I haven't emphasised it, prior knowledge is generally recognised as one of the most important sources of variation between students. So very often, high quality educational experiments will include a pre-test, and we can use that information in what's called analysis of covariance for more sensitive tests of our hypotheses. So one of my favourite techniques in statistics when I can use it. And lastly, sometimes we may have quite complex hypotheses that go beyond just, are these two groups different? We may be testing for interaction effects, like aptitude interaction effects, like expertise reversal, and therefore we need to create experimental conditions that are suitable for testing those hypotheses. As an example, in Ender's research, looking at the interaction between the goal-free effect and cooperative learning. And so to properly test a number of different hypotheses, she needs 4 groups with all 4 cells, all 4 combinations of those 2 variables. So we need suitable design of our experiment in order to test the hypotheses that we're interested in. In other words, moderation effects. Sometimes we are interested in what's called mediation effects, that the effect of independent variable on dependent variable passes through this mediating variable. That's important research because it gives us a richer sense of the theoretical mechanisms for the effect of the independent variable on the dependent variable. So an example would be cognitive load. Sometimes people test, often actually, people present cognitive load as an outcome. Some people argue that we should be treating cognitive load as a mechanism, as a mediator, and we therefore need suitable tests and suitable experimental designs. So, a number of different ways of considering variability and understanding that variability through suitable design and analysis. Everyone, there's a lot on this screen. I just invite you to have a quick read through it, and then I'll make some more comments. So just as some general, I'm just mindful of the time, so I won't spend too much time on this slide, but just to give a very, very big recommendation for this textbook by Rex Klein, 2009. It's called Becoming a Behavioural Science Researcher. It's really, really good for early career researchers to give a sense of what is involved in doing high quality research. I've drawn this model from that textbook. This model talks about 3 fundamental considerations for educational researchers that we need to think carefully about: design issues and the implications for both internal validity and external validity. We need to give very careful consideration to measurement so that we can measure our hypothetical constructs well, reliably, validly. And lastly, that we need to use suitable analysis depending on the qualities of our data. Sometimes our data is a bit messy. There might be problems, and standard statistical methods may not work so well as more recently developed statistical methods. So all of these things, all of these considerations need to be thought of in doing high quality research. I want to give you a few examples to do with statistics. Just so if we look at analysis, okay, so we're focusing on analysis. This result comes from my PhD research many, many years ago. I collected data from school children and they were matched on a pre-test. Okay, so the school gave me a pre-test and I paired those students. So first two students, highest two scores on the pre-test, then the next two, then the next two, then the next two. And within those pairs, I randomly assigned students to one condition or another. When I did a t-test using a matched result, a paired sample t-test, I get the same effect size, but my p-value and my confidence interval are different across the two. When I use a suitable t-test, a suitable form of analysis for my data, I get a more sensitive test of my hypotheses. The confidence interval is narrower. And so if you're used to thinking about probability values, p-values, the p-value in this one would be higher than this one. So just one example of suitable analysis that follows from a design decision. Here's another one. An experiment when I had a covariate, a pretest, a good quality pretest, very reliable. And I was able to use that covariate to achieve a more sensitive analysis. When I didn't use the covariate, just a standard t-test, here's my results. 95% confidence interval that covers 0. In other words, that the p-value would be greater than 0.05. And you might think, oh, the difference between the two groups is not statistically significant. But when I used a good quality covariate testing prior knowledge, the situation changes. Larger effect size, smaller confidence interval. So a more sensitive test of my hypotheses. Definitely worth my time to collect that pre-test variable and use it as a covariate, a more sensitive test. Okay, talking about our measurement concerns. So just to talk through this. Another experiment. I had tests which were based on 20 multiple choice questions. 20 multiple choice questions is quite a few questions. But the result of 20 multiple choice questions is a more reliable measure of what people have learned. As a little experiment, I sampled from those 20 multiple choice questions and created new test scores. So when I used 20 items, my Cronbach's alpha was 0.73. Nice clear effect, statistically significant. If I only sampled 4 of those test items and created a test score, the situation changes. In this case, the result was still statistically significant, but I got lucky. If I only selected items 5 to 8, not statistically significant, and much, much lower Cronbach's alpha. So whenever you have, you should always be thinking very carefully about the qualities of your measures in doing educational experiments. Usually, longer tests are more reliable. Often we don't have enough time to do as long a test as we might want. And so that's the trade-off. Wherever possible, don't just use one question. Use more than one, sometimes quite a few more than one. And those tests need to be aligned with what the students' capabilities are. Okay. Next big consideration, your sample size, an ongoing issue in psychological research. If we only use small samples, we take a big risk. The law of large numbers is a fundamental consideration in all kinds of research. The smaller our sample, the more subject we are to sampling variability, the more error variance there will be in our results. And so wherever possible, larger samples are going to be more useful to us than smaller samples. Again, we don't always have the luxury of a very, very large sample, but wherever possible, it should be a consideration for us. Particularly when we're investigating quite small effect sizes. If we have very small effect sizes, we will need larger samples to have the best chance possible to detect those effect sizes. This heuristic, this rule of thumb, keeps me up at night. If we want to estimate our effect sizes with a great deal of precision, then we're going to need very, very large samples. So, rule of thumb, if we want to reduce our confidence intervals, if we want to halve our confidence intervals, we need to quadruple our sample size, 4 times as large a sample. That's really challenging, and we may not always have that luxury. Okay, what do I mean by a confidence interval? Basically a measure of uncertainty around our estimate. I won't show you the dance of the confidence intervals quite now. Maybe you can have a look at that later. This is a nice demonstration, an online website for showing how confidence intervals change with the sample size that you select. In short, larger sample, smaller confidence interval, more precision in your data. Okay. In good quality educational research, we often see what's called power analysis. Power analysis is a form of analysis that we do before a research study starts. We come up with the best estimate that we can of the likely effect size that we will find, and we plan our study accordingly. We choose a suitable sample size. We might think, okay, are there opportunities to use covariates, which will give me a more sensitive test? Could I use pairing? Could I use more reliable measures than I'm typically using? These are all considerations. Depending on the form of your study, different types of power analysis will be necessary. In a 2-group experiment, power analysis is pretty straightforward. If our studies are more complex, like a factorial experiment, then we need more advanced forms of power analysis. We need to take account of the type of measurement that we have. Measurements, forms of measurement are different. We can talk about 4 different types of measures: nominal, ordinal, interval, and ratio. Usually, the statistics that we use, like analysis of variance, the assumption is that our measures are either interval or ratio. If they're ordinal, we might be on shaky ground, and that we should probably think carefully about, is standard analysis of variance really suitable? If we're using nominal, then that's more like, you'd probably more want cross-tabulation, chi-square analysis, more suitable for that. So we need to have forms of analysis that are aligned with our measures, is what I'm saying. And so there are a range of different alternative forms of analysis that we might use when we don't have interval or ratio measures. Some suggestions here. One problem that we sometimes see in educational research is floor and ceiling effects. A floor effect is when a significant proportion of students achieve the highest possible score. A floor effect is when a significant proportion of students get the lowest possible score. And that results in quite non-normal distributions. T-tests, analysis of variance, they are based on relatively normal distributions. So it's a problem when we have ceiling and floor effects. So as an example from research that published recently, in our ratings of extraneous cognitive load that we got from students, we see large proportions of students giving the lowest possible cognitive load rating. In other words, they were saying, yeah, I didn't experience any extraneous cognitive load. When we did a t-test with the standard measures, the standard t-test, it wasn't quite statistically significant. Standard t-test. But happily, there's a new form of the t-test that you can use when you have floor and ceiling effects. And when I use that form, statistically significant. So I think this is a really important alternative form of analysis when we have clear ceiling or floor effects. And that, in my experience, it happens kind of, not frequently, but sometimes in cognitive load theory research. So a good additional tool to have in the toolbox. All of this discussion basically is around, do the assumptions of your analyses hold? If they don't hold, you may need to reconsider the type of analysis that you use. Sometimes I've been playing with some alternative forms of analysis beyond the classic t-tests, because the assumptions of my data often don't hold. Data are quite clearly non-normally distributed. So some alternative methods. Everyone, a quick zooming out a bit and talking about educational effects again. There's a basic question that we can ask is, well, how big is the effect that I am seeing here? Is this a small effect, or a medium effect, or a large effect? Historically, an American statistician called Jacob Cohen made some suggestions around small, moderate and large effects. He was very careful in what he said, at that time. He said, well, I'm offering these suggestions and that researchers in particular fields should probably think carefully about effect sizes in their own fields. But unfortunately, most people haven't thought very carefully about that, and these effect sizes have been sort of overused. In educational research, a couple of different people have tried to provide suggestions, alternative suggestions to these ones. So an Australian researcher, actually New Zealand, John Hattie, suggests that effect sizes larger than 0.40 might be educationally meaningful. Kraft, in the 2020 review, made these suggestions. But more generally, the field of education probably needs to put a lot more time and effort into considering what is a small, medium, large, educationally meaningful effect. One of my goals in the next couple of years is to do a review of cognitive load theory effect sizes to try and figure out what is the range of effects within our field, so as to be able to make these assessments in a more focused way, so instructional design effects particularly. So get back to me in a couple of years and hopefully I have an answer for you. Okay. There are different types of experiments that we can conduct. Most of the research that I've done is what's called a laboratory experiment, where I basically sit in a room, or one of my students sits in a room with a person, and we do a lesson one-on-one. This type of experiment has very, very high internal validity. There are many, many controls on what happens in that experiment. Often we choose a room that is very quiet, no distractions, and we do the experiment under test conditions, like doing a test in school. Findings from lab experiments are quite dependable, but there's a big question mark hanging over these experiments because they are done under conditions that are very different to classrooms. So can we generalise from these lab experiments? An alternative form of experiment is what's called a field experiment, and that's the kind of research that ENDA does and has done very successfully for a few years now. This type of research is done under more realistic classroom conditions, and that's a real positive because we might take ideas that are developed under careful laboratory conditions and then we see if they work in the real world. So both of these types of research, both these types of experiments have their place. But one of the reasons I'm here is to learn more about how ENDA does these kinds of experiments. Very excited to see. We'll be going to a school next Monday? On Monday, yeah. So wish us luck. So nearly finished, everyone. Just a few more comments about different types of experiments. Usually, remember I talked about random assignment to groups. So we might randomly assign this person to that group, 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 and so forth. Good if we can do it, but sometimes impossible. Sometimes we may have whole classrooms that we want to test our ideas with, and so we give this whole classroom one experimental condition and this whole classroom another experimental condition. That's closer to what we call a quasi-experiment. We can't randomly assign individual kids, we have to randomly assign whole groups. There's some question marks about the internal validity of findings from these studies, but we can try and rule out those question marks through a couple of design decisions like what we see on screen here. So we design that they're as similar as possible. We might use covariates like pre-tests to really test, are the groups as equivalent as we might consider. And we therefore need to take a fair bit of care in making causal claims from quasi-experiments. But it's still a valuable form of research in educational settings. We might randomly, if we have enough money and resources, we might do very high quality cluster experiments. These are beyond just quasi-experiments. Imagine we've got 30 classrooms that randomly assigned to an experimental condition, 30 classrooms randomly assigned to another experimental condition. This is possible, difficult, but possible. And some experiments use this format, like my Australian colleague Jenny Gore, doing quality teaching round studies. Another approach, which is increasingly of interest, is doing studies online, where you can access literally tens of thousands of people. You have to pay some money for it, but you might access students through platforms like Qualtrics or Gorilla, or Prolific would be another one. So another sort of set of possibilities for online educational experiments. Okay, so I'm just checking where I am. Just to emphasise everyone that when we talk about quasi-experiments, there are some other forms of quasi-experiments that I haven't talked about too much. Some of them are used in special education, like time series, or propensity score or regression discontinuities designs. But mostly when I talk about educational quasi-experiments, it's when we randomly assign a whole classroom to one group or another group. Perhaps I should have started here, everyone, rather than finished here. It's important to think carefully about the ethics of our experimental research. And so on screen here, we see a number of the ethical considerations. These should be taken into account when you do an ethics application. So we want to be sure that students and their parents are giving informed consent. If possible, that students are blind to the hypotheses that are being tested, because otherwise they might respond accordingly. We should be using power analysis wherever possible so that we're not wasting resources. If we do underpowered studies, that's kind of a waste of time and resources. Preferably, we should be using pre-registration and of our research design and hypotheses and analytic methods to present p-hacking, and these can be done through the Open Science Framework. So this represents how high quality research is very often done now in educational settings. And so, look, I just want to finish with this quote from one of the giants of 20th century psychology, Kurt Levin. He said, if you want to truly understand something, try and change it. That's what experiments do. They force us to try and understand educational phenomena by changing things, by comparing at least two groups, changing experimental materials, changing lesson materials, changing instructional designs in order to see if those changes have the effects that we believe they will have. So I'll finish there and just mention that there are a number of recommended resources. Again, I will share these resources with Enda, and she will pass them on to you. So I hope that I have made you more interested in educational experiments and given you some ideas for and considerations that you can use in designing your own studies. Terima kasih. Can I invite any questions? Go ahead.
Check. Okay. Thank you for the time. I want to ask about. So in my undergraduate thesis, I compare motivational intervention and presentation format. I will be measuring multiple dependent variables such as transferability, motivation level, and cognitive load.
Yes.
Since these dependent variables are likely correlated, how to choose the right statistical analysis technique? Do you have any recommendation to analyze this type of data?
Yep. That's a really good question. It depends on the sort of the philosophical approach that you take to data analysis. Some people would say that you need to use a multivariate analysis of variance in order to take account of the likely correlations. And I should say, you should start by testing whether they are in fact correlated. But other people would argue that what's important is that you have clear hypotheses about effects, the effects that you expect on all of those variables. So given clear hypotheses, it's not necessary to sort of account for that, for those likely intercorrelations. Those intercorrelations may be, or possibly will be, theoretically interesting in their own right, but they won't require some impact on your analyses, like control of type 1 error rate or multivariate analysis of variance. So my advice would be treat them separately. So I hope that helps. Yeah. Okay. Other questions?
Silakan Bapak Ibu. Would you like to describe to the audience now the history of split attention effect?
Sure.
If
Great question.
if you can recall that was actually a hypothesis that was rejected.
Correct.
And then we develop a new principle.
Yes, thank you for reminding me of that. Everyone, remember early in the presentation, I talked about how if the facts don't fit the theory, so much the worse for the theory, that the theory needs to adapt to the facts. Do you remember me saying that? Enda is referring to the first big challenge in cognitive load theory where that needed to happen. The first two big effects in cognitive load theory were the goal-free effect and then the worked examples effect. Worked examples in the early research used algebra. And then a PhD student started investigating worked examples with geometry and couldn't find a benefit of worked examples compared to problem solving. So what's going on? Our hypotheses are not being supported. And so the way I've heard John Sweller describe that time, they had to sit and think very carefully for a few months about what just happened. What is it about these lesson materials that might explain our failure to replicate. And the hypothesis that they generated was that the split attention between text and diagrams was another source of extraneous cognitive load. And so they then changed their experimental plans to really explicitly investigate whether integrated worked examples led to better learning than split attention worked examples, both of those compared to problem solving. So really, really important early example in cognitive load theory of the benefits of failed experiments. Sometimes we learn, often we learn from our failures as much as our successes, but we have to work through the pain and discomfort of these failures to replicate in order to learn something deeper. So I hope that gives us. So there have been a number of these examples, and John Sweller actually wrote a review paper, I think it was last year or the year before, about how cognitive load theory has benefited from these replication failures because it has promoted new and careful hypothesis tests there.
Baik, that's one example how an experiment and even a rejections of a hypothesis, failures on generating the effect that we hypothesized before the experiment can actually give us more insight or deeper insight on how learning happens. And that's the research in cognitive flow theory, and that's how cognitive flow theory evolves. We evolve by doing experiments, by trying to change, modify, or adapt a design of instructions into many ways, many areas, many topics, adding something here and there. And so I think I remember what you have written in your presentations: to understand something, then try to change that.
That's right. Yep. Yep.
So to understand why learning from, for example, doing self-explanations, how that self-explanation works, then try to add self-explanations, try to change the self-explanation prompts to understand how giving self-explanation works or doesn't work during instructions.
Just to
That's
build
another
on,
way.
Just to build on that, one thing to emphasise about how cognitive load theory has evolved over 40 years is that there is, when you look carefully at the research base, at all of the studies, you can see clear linkages from how early research has informed later research, later research, later research. So I am constantly trying to think carefully about what is my current best knowledge of good instructional design based on cognitive load theory, and can I improve even further on that? So if I design my best possible worked example, what further changes can I make to it? As an example, in my own current research that I'm working with Andrew on, we know how to do really good quality worked examples. So, you know, no split attention, colour coding, segmentation, whole range of different strategies. And my question now is, what if we invite students to trace across those worked examples, to touch the worked examples at specified points and draw with their fingers on the worked example? across, about 10 different experiments now. We have good evidence that tracing specified elements of worked examples improves learning even more than just visual studying of worked examples. But I have based that research idea on high quality worked examples as my control group. So we often use what is the state of the art, what is the best practice for our control group, and can we improve even further on that.
Okay, Bapak Ibu, it's nearly 3 p.m. So we've been here like a couple hours already. Are you okay? How about your working memory situation now? Okay, we have learned so many since morning. So in the morning we have some essential skills on cognitive load theory. We learned about how our working memory might be limited in capacity or maybe in duration too. Do you still remember the numbers that you practiced this morning? Not at all, so it's already gone. That's an example of our working memory is limited in durations.
That's right.
Am I right?
Yeah. I mean, you probably have a general memory for the activity, right? For the digit span activity, but not the specifics of the memory. So memories take different forms, different levels of detail.
Right. So you remember the event, but not the details in it. And that's one kind of memory that we evolved to have or to create in our brain. Okay, and we also learned some instructional strategies. He gave us some examples on the principles on presenting learning materials. He talks about intrinsic cognitive load, extraneous cognitive load, germane cognitive load, and an example of self-rating of cognitive load using the emoticon and the 5 scale point. I actually often use the 9 points.
9 points.
Yeah, so back to you about Ismail. If you want to know more about whether this is, which one it works, the semantic scale, self-rating scale, Likert scale, or others, there are researchers in cognitive load theory that try to modify the scales and propose new ways to measure cognitive load, including the wording of the questions in the self-rating, using mental effort, level of difficulty, or difficulty in which part of the problem solving, something like that, and those measurements are in English. It is also possible for you, for example, if you're interested, to develop in Indonesians, because, culturally we are different, like in a way to understand a concept, because do you know what I mean? Like level of difficulty and mental effort.
That's right.
It's culturally different meaning in here and in Europe or in Australia. So researchers in Indonesia may develop new research, in particular to know what is the best way to measure cognitive load for Indonesian students.
Yep.
By using experimental design, comparing this scale and that scale, and then modify again, how about if this scale and that scale, and then you analyze the data using covariate or without covariate. It really depends on your experimental situations in laboratory or in a real classrooms. It also depends on your situations. Comparing two groups or more than two groups, so F-test or T-test, it also depends on your experimental designs.
Yep.
Okay. So, he also mentioned to us regarding tracing effect, okay, just now. He mentioned about tracing effect. One of my dissertation students also studying tracing defect. Tracing is like this. You know, when you're looking at a map, you use your fingertip to trace, oh, this is a river, you know. Sometimes you do that, right? This is a mountain, this is the river, this is the road. I'm going from here to here, turn right, turn left. That is tracing. Which one is better? Using fingertip to trace while studying, or just looking? Or pointing? Mountain, river, mosque, or pointing? In mathematics, we often use diagrams, manipulatives. That is also a source or an idea for you to study or to research about the principles of using tracing or pointing, which one works better for our students.
So for those, for students in the, is it Friday, I think, that the advanced
On
cognitive
Friday,
load?
yeah.
So,
He said about that on
yeah,
Friday.
so I'll be doing another lecture on sort of advanced topics in cognitive load theory, and I will
That's
talk...
on Saturday.
Saturday, sorry.
Saturday.
So on Saturday, we will talk some more about some of these advanced topics like embodied cognition, using principles of evolutionary educational psychology for as a source of new cognitive load theory ideas. So more to come on that. So today was more historical cognitive load theory, and more to come on some advanced topics on Saturday.
On Saturday. So on Friday, there will be proposal seminars from one of my dissertation students, and his topic is on tracing. And on Saturday, he will have a talk for all of us about embedded cognitions. I'm trying to connect your concept with deep learning.
Yep.
And tell them about this. So you know that we are now given a view that learning should be deeper than just in the surface area, right? So we will have more chances to transfer our knowledge when we are able to learn into deep area, not just the surface area. Okay, the question is that how to do deep learning, and is it possible, or when we use our embedded cognitions, would it happen that we deep learning rather than surface learning? That's just one example of the questions that you can raise to start research on instructional design and cognitive load theory.
Excellent.
Okay, thank you. Okay, is that all? I think, yeah, it's 10 to 3. So we may have more discussions informally after this. It's you are very welcome, and again, it's a great honor for us to have you here, and we having your knowledge on cognitive load theory and the experimental designs.
You are very welcome, and thank you once again.
Thank you
for
very
having
much.
me.
Bapak Ibu, big applause to him. Terima kasih untuk Bapak Ibu semuanya and students. Thank you very much. We hope you have the big benefits of this event. Hopefully you go home with a lot of ideas, but please maintain your working memory capacity. Make sure you do interleavings or something to relax your brain, and yes, I wish to see you in the next events. Thank you very much again. Terima kasih.
Terima kasih.
Oh, there is a token of appreciation. Yes,
Oh, wow.
indeed. For him. Okay.
Oh, goodness.
Should we stand there?
Oh, yeah, sure.
Or
Okay.
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 Yeah.
Sorry, what? Oh, okay.
Bapak Ibu mohon menyaksikan pemberian ini ya. Ini benar dari fakultas, jadi sudah saya serahkan kepada beliau. Thank you, Paul.
You're very welcome.
We will wrap this up for you.
Sure.
Thank you very much from the presentation, the insightful presentation from Paul Keynes, and also the emphasis from Ibu Ender and Nawati. Okay, because Ibu Ender and Nawati have to close the presentation, yeah. So I'm sorry if we have any incorrectly statement, but I hope you guys always happy and enjoy the presentation. And don't forget about the Saturday event, that the brochure, the blue brochure. Okay, yeah. Thank you very much. I close this presentation. Wassalamualaikum warahmatullahi wabarakatuh.
It's beautiful cloth.
It's also batik.
Oh, yep, lots of batik. I better get this one.